By day, Miss Weber is a biology teacher at Albemarle High School.
This is what we need to focus on. Okay? All right, are you good? Oh, thank you.
But when the bell rings, she becomes something much, much more. That's when she transforms into Dr. Science. She searches the globe for interesting research to bring back to her students. Today, Dr. Science will sit down with Dr. Song Hu, an assistant professor of biomedical engineering at the University of Virginia. Dr. Hu's research focuses on a recently developed technology to detect, image, and possibly treat cardiovascular-related diseases in the human body.
So the diseases I'm targeting are stroke, as I mentioned, Alzheimer's disease, cancer, and also some cardiovascular disease like the atherosclerosis. Yeah. So these are the major diseases I'm targeting.
The new technology that Dr. Hu is using is called photoacoustic microscopy.
And actually, my technology can image the vascular anatomy, function, metabolism. So all these are key parameters that can quantify the disease progression and also the potential therapeutic mechanisms. By saying the name, photoacoustic, so you might be able to guess what you're going to do. So actually it's a combination of optics and ultrasound. So the photo part represents optics, and the acoustic part actually represents ultrasound. So actually this imaging technology combines optics and ultrasound. So the way it combines these two physics is that, so here we use laser light shine into the tissue. The tissue will absorb the light, so it will generate transient heating. So this transient heating will cause the tissue expansion. So if the tissue expands and then shrink later, so it will generate this mechanical wave. So the mechanical wave will propagate inside the tissue in the format of ultrasound. So if we play the ultrasound detector outside the tissue, just like commercial ultrasound machine in clinic, so we can listen to the heat generated inside the tissue. So what we do is that we actually use ultrasound detector to listen to the optical absorption generated inside tissue.
Dr. Hu can then create striking images. His imaging technique can reveal oxygen concentration of blood in a mouse's ear. Veins are green and arteries are red. He can also image the hemoglobin concentration of blood vessels in a mouse's ear. The images are so detailed that single red blood cells are observable. Images of the vascularization of mouse brains and irises of mouse eyes are more examples of the possibilities of photoacoustic imagery. Dr. Hu relies on differences in tissues to create these images.
They can absorb light at different amplitude, or they can absorb light at different wavelengths. So by doing that, actually you can distinguish different type of tissues by their absorption signature. So each one has a different signature. That's how you can distinguish different part of tissues. For example, cancer, particularly renal cancer, they are highly angiogenic. Highly angiogenic means they develop a lot of very dense vascular network. And these are blood vessels. They have hemoglobin. They absorb a whole lot of light than other normal tissues. So if you use our technology, actually we can see more absorption from the cancerous tissue than the surrounding normal tissue. So that's how we can distinguish cancer from normal tissue. That's how we can detect cancer in early days.
There are two main branches of photoacoustic imagery that enable scientists to create images of human tissues, like this one, of the blood hemoglobin concentration in a human finger.
So for photoacoustic imaging, we have two different branches. One is called a photoacoustic computed tomography or photoacoustic CT. So we have known, X-ray CT in clinics. So photoacoustic CT works in a similar way. So it puts scanners surrounding the body, and then we shine laser light into the body. It will generate ultrasound signal, and then the detector surrounding the body will pick up the ultrasound signal for imaging. So this is a photoacoustic CT. For the other branch is the branch I'm working on is called photoacoustic microscopy. So it's similar to like the conventional light microscopy we use in biology class. So here you have this optical objective or lens to focus the light into the tissue, and here we have an ultrasound signal on the ultrasound detector on the side to detect the ultrasound signal. So we put the tissue sections beneath the scanner, or we can even put human skin. Although our penetration depth is not very great, it's like 1 millimeter, we still can image skin cancer very well with high resolution. So what we are doing is to, if we have a patient has a skin cancer, we can put the skin, let the patient sit there, and put the scanner on top of the skin to look at the details of the skin cancer. So this is another technical branch that we are working on. So I think within 5 years, we should be able to say the commercial products, and so likely, I hope within 10 years we might be able to say, some prototype stuff in clinics. Actually, one more thing I want to comment on is that currently we are working on. Actually, my advisor, my previous advisor, he is working with a big company, Philips. So they are working together to develop a clinical system for breast cancer imaging and screening. So they are currently doing clinical trials. So if everything goes on smoothly, I think within 10 years we should be able to say some first generation systems that helps physician for diagnosis in the clinic. Well, that's my hope. Yeah, I think that
there are still some ways photoacoustic imaging can be improved to increase the impact this new technology has on the medical field.
Biomedical research. The first thing is that our technology is relatively new. So although the technical strength is demonstrated, but it's still, there's still some way, still some distance from this real, commercialized product. Because our currently our imaging technology, the system is still slow in speed. So if you scan too slowly, so imagine how would it catch fast dynamics that happens inside the body. So, and also in clinics, if the imaging speed is too slow, so the patient will move. So the motion artifact, this is a big concern. So the first thing is the imaging speed, and also the penetration depth, the imaging depth. So here, the technology I'm working on is called photoacoustic microscopy. So it can only penetrate a millimeter inside the tissue because of the high resolution we want to maintain. So now we are asking for more. So we want to extend the penetration, but we don't want to lose the high spatial resolution. Yeah, because we still want to see fine details which can tell more about the fundamental insights. So we want to keep the high resolution, but we want to extend the penetration depth.
As the day comes to a close, Dr. Science must hang up her lab coat to prepare for another day at Albemarle High School.